Thank you. Is this on? Do you hear me? Yes. Okay, so thank you. So my name is Ragnhild. I'm at Stockholm University, and I'm going to tell you about superluminous supernovae. And I apologize if the phrase 2 decades in the title is making anyone feel old. Yes, it has been that long. Oh, that's weird. There's sort of a imprint on the screen. Is this something we're worried about? Anyway. We'll see if it goes away. If not, someone will fix it, I am sure. So the assignment, so to speak, for this talk was to talk about peculiar supernovae, which is a giant topic. Like almost every supernova is peculiar these days, it feels like. And so, one way to approach this is to start with just what is even a normal supernova? So one way is to look at this kind of luminosity timescale diagram. And, we can put these sort of textbook supernova classes into these boxes, right? So we have, for example, type 1a supernovae, which famously have a relation between their luminosity and timescale that makes them useful standardizable candles for cosmology. And we have our core collapse supernovae, which fall into this other gray box, that are kind of your other standard types of supernovae. Of course, this is a idealized diagram. A real data looks a lot messier. So here is an example of this sort of phase space with actual data from the first few years of the ZTF Bright's transient survey. And you do indeed see your 1A supernovae and core collapse supernovae, etc., roughly where you expect them to. But you also see a lot of things outside of those areas that you might very well call peculiar. You have fast transients, you have faint transients, and this is even just optical. We're not even getting into other wavelengths, etc., right? But for the purposes of this talk, what I'm going to focus on are the things sort of up in this top right corner. So we'll hear more about faint supernovae. We'll hear about luminous F-bots, etc. later. So I'm going to talk about mainly these superluminous supernovae. And my hope is to, inspired a little bit by Igor's talk, actually, to also, where relevant, highlight some lessons learned, I guess, that might also be helpful for your favorite peculiar transient. So let's start off with, why is this part of parameter space interesting? Why have we, ever since we found them, tried to basically figure out what are these things? I think what first really caught the interest is that these transients are brighter than you really expect supernovae to be from a standard physical model. And in particular, the amount of energy is more than what you can get out of sort of a normal neutrino-driven core collapse explosion. We're talking radiated energies of the order 10 to the 51 ergs. And also, unlike gamma ray bursts, for example, there's no, at least direct evidence that there's a central engine. We don't see any X-ray emission or gamma ray emission or evidence for relativistic ejecta in the spectra. Really all of this is coming out in the UV optical infrared. And so there's a couple of contenders, basically, for how to make this. So now on the right-hand side, I've sort of zoomed in on this part, and also now these, you can see the sort of spectroscopic labels here. So there's kind of 3 main contenders, I would say, for how to make a superluminous supernova. One is circumstellar interaction, so basically converting kinetic energy into radiation. This is definitely at play in many of the hydrogen-rich ones we see. We could have a central engine, and my favorite central engine, and possibly your favorite central engine too, is a magnetar. But when I say magnetar, in this case, really what I mean is essentially a light bulb that I put at the center of my ejecta, and that spins down with a certain time scale. And in particular, the kind of magnetar I need to make a superluminous supernova is in the sort of 10 to the 14 Gauss regime, because really what I need to make a very optically luminous transient is something that spins down over a long time scale. So not so fast it makes a GRB, but sort of long enough it injects energy and can make something very optically luminous. And then finally, the third thing that can make something this luminous is just if you make a ridiculous amount of nickel-56. And so there is a regime, or there is a model, pair instability supernovae, that could also do this. And I will get back to those towards the end of the talk, hopefully. So in terms of lessons learned, I will say, being a bit introspective, one of the main things we've learned is, trying to define a new class of anything with only a few examples and without like a good physical understanding of what you're seeing, it's hard. We started these plots are from a review paper by Avishai Galyam that came in 2012. And it sorts things very neatly into three categories, actually. So you have your type 1s and your type 2s based on hydrogen. And he also has a third class, which are supposed to be pair instability supernovae, essentially. And he draws this neat line at -21 absolute magnitude in order to define these objects. And that worked really well for the sample size of a few. That existed at the time. But what has happened since 2012 is basically huge advances in transient surveys, right? So back then, we were mostly looking at data from Pan-STARRS, and PTF had just got it started. We've seen versions of this plot already. And I think the real game changer here has been ZTF. And so a lot of the results I'm going to present during this talk are from ZTF, partially because it's what found the most superluminous supernovae, and it also just happens to be the survey I've been working with for the past decade. So ZTF really has changed this landscape quite a lot in terms of our understanding, and I'll walk you through it. Now, I'm an observer, so if I'm going to talk about how do we currently define superluminous supernovae? It's going to look something like this. So it's still fundamentally a photometric definition. It's based on luminosity, but where that threshold is has kind of crept downwards over time as we find a lot of things that are fainter than -21, but still spectroscopically and otherwise look very much like the same thing. And whether or not it even makes sense to draw a sharp line is not really clear, honestly. But let's draw a line around -20, then we can also ask, okay, is there hydrogen or is there not hydrogen? We can divide them into type 1s and type 2s. One thing we've learned from ZTF is some of these type 1s also have helium. So there exists a class of superluminous 1b's. But most of the hydrogen poor ones, I guess we would spectroscopically call 1c's. Type 2s, you can also further subdivide into whether they spectroscopically looks like 2n's, essentially, whether they have these characteristic line profiles, narrow core Lorentzian wings, or whether they have broad or even P Cygni profiles. I'll get back to that a little bit. And there's even a few that don't show hydrogen at peak, but show hydrogen at late times. So they have been called 1.5. I don't have time to get into those, but they're interesting. So I guess one of the, again, getting back to sort of lessons learned, one sort of word of caution I want to say is trying to find trends when you're looking at sort of small samples, and especially if you're trying to compile everything from the literature from different surveys, etc., is dangerous. And I think a good example of this are these attempts to standardize superluminous supernovae. And I think it's a really good idea to try to do this. These are the transients you're going to see to the furthest. It would be amazing if we could standardize them and use them for cosmology. And, early efforts were pretty promising. So this is work by Cosimo Insera, working with a literature sample and trying to find these various relations between time scale, color, luminosity in different bands. And it looks kind of nice. And then you apply it to something like the dark energy survey sample. And, so those are the same bands and the actual sample overplotted. And it just does not work at all, basically. So it looks like superluminous supernovae are not standardizable, sadly. Another thing that is different from if I was giving this talk 10 years ago, basically, is I would say prior to ZTF, we were doing a pretty good job at fitting most superluminous supernovae light curves with these simple magnetar spin-down models. So this is an example, just a few light curves from a paper by Matt Nicol, where they basically took the then very new MOSFET code and applied it to the entire sample, and it worked pretty well, actually. But of course, if you look at these light curves, not all of them are fantastic, right? There's big gaps. Some of them, you only have a rise, some you only have a decline. The cadence might be spotty, etc. And so actually, sadly, the lesson here is that more data is a blessing and a curse. Sometimes it just ruins everything. And because actually, if you look at the ZDF sample of type 1 superluminous supernovae, there's a significant fraction that just completely failed to be fit by a magnetar model. So about 2/3 of the sample, you can get a sort of satisfactory magnetar fit. But I'm showing here the sort of 25% or so of light curves that either have these significant bumps and sharp drops and things, or they have this inverted V shape that you just can't get with this magnetar diffusion. Or in some cases, the rise is long, but the decay is short. And all of these are basically very hard to get when you have just a central engine source and diffusion. So I'd say one thing we've learned from ZTF is we cannot fit them all with magnetars, at least not with your standard magnetar, or only with a magnetar. That is not to say that all of these are necessarily powered by circumstellar interaction, or that you should believe the parameters that come out of the CSM parametric model. But it's saying, the sort of the simple model kind of fails at ZTF cadence. And in general, actually, one thing we are learning is that again, once you have better data, these light curves are generally not all that smooth. Some have rebrightenings, many have these kind of bumps or sort of shallow undulations on top of the main light curve. This is it might not show up so well on this projector, on this plot, but basically throughout the entire decline of this light curve, you have this sort of wavy thing going on top of the main decline, and it's across all filters. It turns out this is not that unusual, and it's another thing that it's hard to explain with a central source, at least at early times, where sort of the time scale of this variability is faster than your diffusion time. Sort of continuing on the, one thing that can sort of naturally make this is if you have some amount of circumstellar material that you're running into that's modulating your light curve. And I guess sort of continuing on the trend of circumstellar material, going back to also I really liked Igor's point of catch something unexpected, and if you do, run with it. So this is an example of that. So this is a zoom in of the spectrum of the superluminous supernovae IPTF16EH at the magnesium-2 doublet. And what you see here in this near-peak spectrum is two absorption systems. So you have your one that's at basically the redshift of what we think is the host galaxy, and then there's a second system that's slightly offset, is slightly blue shifted. And that is in itself not extraordinary. You see multiple absorption systems in the universe all the time, right? It's telling you there's some other gas along the line of sight. But we were following this supernova with Keck to late times, and things started getting weird. So as the supernova faded, we started seeing the same magnesium-2 line, but now it started showing up in emission. So this is 100 days after explosion, and nearly 270 days after explosion. Now the supernova continuum has faded a lot, so you're basically almost only seeing the emission. And 300 days after explosion. And those with a keen eye might also notice something even stranger, which is that the wavelength of this line is shifting. So it started out blue shifted, and at the end it is red shifted. And after this, it faded away. And this is actually beautifully, simply explained by a resonance line scattering light echo in a circumstellar shell. So what we are seeing here is CSM shell that's traveling at basically this offset, about 3,000 kilometers a second. At peak light, we're seeing absorption, like a supernova spectrum with absorption, like blue shifted absorption lines. And then as the supernova fades, we see the light echoes sweep across the shell, basically. So we first see the emission from the blue shifted side that's closer to us, and then we see the emission from the red shifted side, basically, that's moving away from us, and then it fades away. So this was really cool. We could constrain a bunch of properties about this shell, like that it was ejected about 30 years before the supernova exploded. It's moving at this 3,000 kilometers a second. But it was a single example, right? So you might wonder, was this just like some crazy lucky catch, or is this normal? And another thing we then realized is we could have recognized this even at peak light if we'd had better resolution data, just from that double absorption system. And this led to a systematic search for these kinds of shells using the extruder instrument on VLT. So this was the basis of my student Anna Maria Guinness' PhD thesis. So we had a dedicated program for several semesters, basically looking for these extra absorption systems. And then we also went through basically all of the extruder spectra of superluminous supernova in the literature we could find with sufficient signal to noise. And we were able to find a total of 5 more examples. So, this is not super common, but it's definitely not unique. Like a significant fraction, a few tenths of % of type 1 superluminous supernovae seem to have this. Here is one of the more striking examples. So this is what these absorption profiles look like with extruder. So again, you see the narrow system from the host galaxy, and then you see this time the resolved line profile from the circumstellar shell. It's the doublet is a bit blended, etc. But what's nice about this data is we can actually use the information in this line profile together with some modeling that we did in collaboration with Klaus Fransson to basically say something about the shell properties, because this is going to look different if the shell is moving faster or slower, if it's a thinner shell or thicker shell, further in, further out, etc. So what we found, or I should say what Anna Maria found, was that these shells that we found with extruder are generally ejected on sort of timescales months to years before explosion. And that is partially perhaps a selection effect because we found they're easier to see when they're further in, basically. But they're also sort of clustering in velocity space around 3,000 to 5,000 kilometers a second, which to me is very, very fast circumstellar material. Like that's an eruption, basically. And one of the physical processes that could do this is the pulsational pair instability. So that is one intriguing possibility, but then leads to the next question of, if this was like a 50 solar mass helium core that had this eruption right before, then how did it explode? Because those stars are supposed to make black holes. Maybe there's rotation. It's an open question. So far, I've spoken about type 1 superluminous supernovae. And this has kind of been a thing in the community. We've mainly focused on the type 1s for, I think, various reasons. They're sort of a bit more mysterious. In these earlier surveys, like Pan-STARRS, for example, the type 1s were a lot easier to find because as you move to higher redshift, you lose H-alpha and you just can't classify them. But with ZTF, we have actually discovered large amounts of hydrogen-rich superluminous supernovae, and so we finally put out these samples. The majority are spectroscopically type 2N, so you could think of them as the extreme end of the sort of interacting supernova population, but still requiring, extreme mass loss, basically. Like, what kind of stars are these? And there's also a subclass that don't show 2N light profiles. They have broad Balmer lines. Whether those are still interaction powered or something else, I think it's still an open question. One thing I do want to say is this is also an example where it's hard to make a meaningful definition, basically. Like, if there's no sharp boundary, what do you call one thing or the other? But I also want to say, I don't think we should ignore the type 2s because they're definitely there in your data. And we're very much moving towards these large photometric samples. And so if you're very just focused on this thing you are looking for and you ignore that there's another thing that looks very much like it, then it's nice to have that sample also in your training set, let's say. See, I don't have time to really go into detail about the type 2s, but I do want to refer you to these ZTF papers. One thing to say, these are also a fairly diverse population. Some are extremely luminous, some are sort of barely above this -20 threshold, some are fast, some are slow. Some have these pretty dramatic bumps, so telling us they probably also had a kind of eruptive mass loss history, let's say. Another sort of question, is can some of these superluminous supernovae be pair instability supernovae? Because that is, in my opinion, one of the most interesting transients in this sort of luminous, long-lived regime. So this is the predicted fate of stars of 150 to 300 solar masses or something that build up cores heavy enough to encounter this pair instability, and you blow up the entire thing. They're a lot more relevant after LIGO is starting to map out the black hole mass distribution, because one of the main predictions is, if pair instability supernovae exist, they should make a mass gap basically in the black holes, which I think we're starting to see. Now, alas, most superluminous supernovae are not pair instability supernovae. They basically have two fast timescales. So one of the hallmarks of a pair instability explosion is just you have this enormous ejecta mass, and that gives you a very long diffusion time and a very slow transient. We have some intriguing candidates. The one shown here is supernova 2018 IBB. So the sort of black dots and black line is the light curve, and then overplotted are some of these pair instability models. So the light curve is actually a really nice fit. The elephant in the room, again, is actually circumstellar interaction. So this transient was just basically much bluer than the models, and it shows direct evidence of having, actually it had one of these CSM shells. It's one of the 6 that has one. And you see the supernova running into that shell and interacting with it, and it's changing the color. So maybe also our models are just incomplete of what these stars do. So we have a whole session on host galaxies tomorrow, but I will say, one thing we've definitely learned is, yes, having contextual information, having host galaxy properties is extremely helpful. Type 1 superluminous supernovae show a very strong preference for star-forming metal-poor, low-mass galaxies, basically, which more so than any of these models actually tell us that the progenitor has to be a massive star, and it's probably low metallicity. There's no other way to explain this trend. Type 2 superluminous supernovae are found over a much bigger range of galaxy properties, and this more or less holds up with the ZTF samples as well. So this is a plot from Dan Perley's 2016 paper from the PTF samples showing sort of stellar mass versus star formation rate, and you can see the type 1s sort of off to the left side, basically. I think I have one more minute or something. I want to mention this I think this is another cool result that came out of this X-shooter sample, actually, because when you have really beautiful data and you have both emission lines and absorption lines, you can also do some cool galaxy science. So this was work done in collaboration with Alberto Saldana Lopez and Matthew Hayes at Stockholm University, using, again, now the magnesium-2 lines from the ISM in the host galaxy together with the emission lines, basically, to model these line profiles and use them to constrain the outflow properties of these very low mass galaxies that are otherwise basically inaccessible for dwarf galaxy surveys. And what we found was that these kind of lie below this canonical outflow velocity star formation rates relation, and I think the implication is that most of these outflows are basically stellar wind driven rather than supernova driven. So these are it's consistent with the idea that these are some of the first stars to explode in a starburst. We've not had many supernovae to sort of launch these bigger outflows. And I think to the extent that there's a lesson here is also, it's good to talk to your colleagues who work on sort of similar but different things from you. They might also have a use for your data. And of course, LSST is here. As Igor said, we're already in the data-driven era, and it's only getting worse. We need automated tools, basically, to help us deal with this. So I encourage you to check out the poster that is currently up by Etienne Rosset about the work he's doing on finding superluminous supernovae using machine learning tools. And with that, I just want to leave you with a few takeaway points. So first of all, I suspect this is true of many peculiar classes, like arriving at a meaningful definition is hard. In this case, I think we've seen there's no sharp gap, but if we draw a line at -20 magnitude, then, ZTF alone has found hundreds of superluminous supernovae. The general energetics of the hydrogen poor ones can be fit by magnetars, but I would say like these sort of detailed light curves definitely cannot. And perhaps related to that, it seems the circumstellar environments of these type 1 superluminous supernovae are rather messy. So we see these bumps, rebrightenings, a non-negligible fraction have CSM shells. This is probably something that needs to be incorporated into the models. I want to remind you, type 2 superluminous supernovae exist. They're actually quite interesting in what they're telling us about the extremes of mass loss and interacting supernovae. We are starting to see some intriguing pair instability candidates. Of course, if they exist, then Rubin should find many. So this is really just starting. And I want to, we always say we want more data. In some sense, like, I don't know that I do, or at least I don't think I need more light curves. I want better models to fit the light curves I already have. And then I want data at other wavelengths, like JWST, for example, would be fantastic to sort of break some of these deadlocks that we have. But I think this is an example where like we keep finding new things and modelers are catching up continuously. It would be nice to have some predictions rather than post-dictions that we could test. So I'll end there. Thank you.
Okay, thanks for the nice review. Any questions? Yep, sit there. I'll let you choose between yourselves.
Hi, thank you for the great talk. I know nothing about superluminous supernovae, so this has been really interesting. I had a question about the magnetar aspect. So I assume that in the magnetar models, they're all doing very similar things, right? But I guess now we know from like FRBs and from like short GRB modeling that some of us have done, there's like clearly a huge range in the behavior of what magnetars can do. So is this something that, I guess, is this considered in the magnetar models, or is it just kind of one thing that's going on? They're like, we will try and model as many with this one go-to.
Yeah, so most of the work that's been done has really just like considered, I mean, we call it a magnetar. It's really a light bulb that follows like a dipole spin down prescription, and you assume all of the energy is thermalized and you ignore any like magnetar physics. I mean, Nikhil is trying to do this better with Redback. So, you should talk maybe. He would know more than me. But yeah, no, it's absolutely like, I mean, magnetar is only something that gives you this like nice time-dependent energy injection, but we ignore everything else.
Nice.
Yeah.
Okay. Thank you.
Yeah, thank you very much. I wanted to ask about the parent stability supernova stuff. So you're saying, you're limited by models and not the data, but what data signature would be a big smoking gun for this? Like the long diffusion times, there's many different types of transients that can do this. That's not obviously definitely a parent stability supernova. What one thing, if you saw it, you'd be like, bang, that's me, that's my parent stability supernova?
So unfortunately, what I want is nebular spectra with James Webb. That's going to be hard.
We can do that, right? No?
Yeah, no, we're trying. Accept our proposals. Yes.
But so what are you, my question then is, what are you looking for specifically in there that ties you
But, like,
definitely to a parent?
one of the things that's very different in a sort of core collapse and a parent stability is the nucleosynthesis. And it turns out the infrared is a cleaner place to look, basically, especially if you have this ongoing CSM interaction that's sort of messing up the optical. So yeah, like there are specific models, and like we're working on better models in Stockholm as well. But I think that would be the way to go.
Thank you.
On over there.
Very intriguing, this double absorbers, magnesium 2, very close, but 3,000 kilometers per second. It's far away, plus these lines are narrow. That means maybe they're not very close to the source. But you have another case that looks really strange because it's broader and it's blue shifted, very intriguing. But I wanted to say that that reminds me a lot about gamma ray bursts. You know that?
Yes.
There's a large fraction at high redshift where you clearly see double absorbers, sometimes close, sometimes far away, thousands of kilometers per second.
Yeah.
But they're narrow lines. They're interstellar low ionization lines. They can be that close to the source, and it's intriguing. Where do they come from? So it reminds me a little bit of this, and it's really fascinating. Thank you.
Yeah, absolutely. Like I know, and actually, like this is something I've on and off been discussing with GRB people, whether they ever see something like this. Because indeed, had we not seen the light echo, we would just have assumed this is just another absorber along the line of sight. That's not that strange. But yeah. Is
the time. I think we'll have to move on. Yep. So let's thank again. Yeah. In the matter, you have the responsibility. Okay, and our next speaker is Daniel Paradiso, who'll be talking about shock formation and evolution in failed supernovae. So, over to you. Thanks.
Yes, hello. I'm Dan Paradiso. I'm a fourth-year PhD student at Syracuse University in the US. I'm going to talk a little bit about the theory of shock waves in failed supernovae, so a bit more on the prediction side of things. So if you'll bear with me for a second, I just want to go over sort of a caricature overview of the core collapse process. So in supergiant stars, you form an iron core. You lose pressure support in the core, it rapidly collapses. You form a neutron star. The neutron star bounces, you form a bounce shock, the shock stalls, but is then revived through some mechanism. One of the most viable mechanisms being the neutrino heating mechanism. And so while most of the neutrinos stream out of the star unimpeded, a small fraction get absorbed in the post-shock region, it reaccelerates the shock, and then it explodes the star. And that's my theorist interpretation of photons, if that was not clear. But you can always ask the question of what happens if the shock doesn't actually get revived. So you still have accretion through the stalled bound shock. Eventually, the neutron star reaches the TOV limit, you form a black hole, and then the star eventually just collapses in on itself and sort of disappears. And this is a very simplistic picture of what I would call a failed supernova. So we do have some evidence that this does happen. Right, so the classic picture on the left, the red supergiant problem. Also, top right, I don't know how to use this. Top right, we could be having these failed supernova given to the primary mass distribution of gravitational wave sources. And then also with numerical simulations, we see that there's these islands of explodability. And then also, we have two candidates of failed supernovae. So the jury is still out on this, but the oldest one being the Adams 2017 source, where you see the star just disappear over time. And then more recently, we had a similar thing go on in M31. And so this picture that I painted so far, and also these images themselves, just sort of show that the star disappears with nothing really happening. But ideally, we would have a way to detect these failed supernovae, these stars disappearing and forming black holes as a transient event. So to go back to the core collapse process, the star itself doesn't just immediately collapse, like I was sort of saying before, and instead it's communicated via a sound wave that moves out through the star and causes material to fall in. So this is normally an animation, but I'm just going to click through it quickly, and you can kind of see it. The sound wave moves out, and it tells material to fall back in, and then eventually accretes onto the black hole. However, while that's happening, and like I was saying before, the neutron star radiates something like almost a half a solar mass in the form of neutrinos, and only a small fraction get absorbed in the post-shock region. So most of the neutrinos just stream out of the star unimpeded, and what that acts as is an almost instantaneous reduction in the gravitational field. So the simple analogy would be if you reduce the mass of the Earth, we would feel a change in G, the atmosphere would feel it. And so now, all of a sudden, I have this velocity boost, which causes the sound wave to steepen into a shock, and a weak shock at that. So just to give you a better picture of this, this is the velocity profile. So initially, you have a sound wave moving out into a hydrostatic medium, and then I have some mass loss, my wave steepens, and it continually steepens. And then over time, you form the shock. And you get this really dynamic picture. So you have a weak shock wave, you have some non-hydrostatic ambient medium that responds to the mass loss, and then you also have accreting material in the interior onto the black hole. And so this is very distinct from other solutions like the Sedov-Taylor solution, where you actually have a really strong shock wave, which makes it harder. So some of the standing big questions on this neutrino mass loss shock propagation is, how does it evolve with time? How do you actually incorporate the mass loss? How is it related to the mass loss? And then also, how is it related to what's the outcome of depending on the stellar structure? And so, again, sort of a simple picture, stellar structure. Supergiants tend to have sort of piecewise power law profiles, which for theorists and observers, power laws are great. You can kind of squint and make out some power laws there. So this is just a 15 solar mass red supergiant of Volva Mesa. And then also yellow, blue supergiants display similar behaviors. So we have new self-similar solutions. So again, like the Sedov-Taylor solution, but very distinct, that relate all of these factors together. So the density profile, you have accretion onto the black hole, and it also relates the strength of the shock to the amount of neutrinos that you lose. So on the plot, the real only takeaway that you need to make on this plot is that the vertical axis shows the Mach number of the shock, which is like 1, a little more than 1. And then the horizontal axis is the mass loss, but actually the relative mass loss. So you can think of delta M being the neutrino mass loss and big M being the mass of the star. And then for a purely mathematical reason, these solutions have sort of a critical mass loss, which I'm just saying this because it's going to be relevant for the next slides. And so there's 2 separate regions that you have to look at. This critical mass loss ends up being like at most 0.1 for the relative mass loss, so like a tenth of the mass of the star. And you get different growths of the shock waves in these regions. So for the subcritical solutions that I'm calling, they grow as a power law in time, a very weak power law. And then in the supercritical, they grow as the log of time or shock position. So in both scenarios, you are essentially not strengthening at all. So this is just a comparison between the analytic solutions and numerical simulations. So the dotted curves are numerical simulations, and then the sort of faint curves are the analytic predictions. And again, what this is showing is that you initially start out as a shock or as a sound wave. You form a shock, but the shock that you form is extremely, extremely weak and essentially nothing more than a sound wave. And again, this is just a different plot, same thing. But what it's showing is that these solutions are converging to the self-similar solution over time, but it takes many, many decades in radius to do so. So very, very weak, unfortunately. And then the supercritical solutions, again, are weak, but they continuously strengthen over time. and are diverging logarithmically. So, okay, what are the actual real-life implications for failed supernovae? So, numerical analyses of this problem have shown that red supergiants sort of easily eject their outer envelopes, and you can eject, a solar mass or so of material, and that's why we tend to look at those for failed supernova candidates. But how, if the shock waves are so weak, what I'm showing is that they're so weak and they grow so slowly, do you actually produce a strong explosion? Because what you end up getting from red supergiant simulations of this problem is that the shock wave is more like in the Sedov-Taylor regime. So it's because I was a bit cheeky, and I was saying that the M that shows up in the solutions is the mass of the star. So if you look, this is delta M over M of those three different stars that I was showing before. And at the surface of the stars, those values are all similar. However, if you actually make this a radially dependent value, then red supergiants have very, very high sort of relative mass losses in the interior. What that means is that the shock is just continuously strengthening over time and should grow very rapidly, and then that's how you end up getting into this regime. So I'm going to leave up a summary. Future work, obviously, comparing these to more realistic simulations of using stellar models and actually doing the core collapse process in neutrino radiation. With that, I'll take questions.
Great, thank you. Any questions? Yeah, Tom.
Thank you for the nice talk. I just wanted to ask, do I understand correctly that this study and these self-similar solutions only account for the effect of changing gravity, let's say, because of the mass loss in neutrinos, but they do not factor in that this part of these neutrinos are going to energize the shock, at least weakly? No?
Yeah, like it's a little bit less than the value that I'm showing there, you mean?
I mean, if the neutrino heating was accounted for, would this contribute?
It would. I mean, the amount of neutrinos that end up getting absorbed by the shock is still only like a couple percent or so. So a little bit for sure. Yeah.
Thank you.
There's two up there. Who's first? Maybe you can.
It's maybe a simple question, but I want to just make it clear. Do you consider here neutrino oscillations and mass loss in neutrinos, meaning that they do have mass, or is just the mass of the stellar envelope ejected that you call mass loss in neutrinos? I mean, I'm confused a bit, so that's why I'm asking.
Yeah, I feel like I didn't hear it that well. You're saying that
Do you consider neutrino oscillations here?
No, not at all. So this is
Flavor oscillations.
the simulations that I was showing were just purely hydrodynamic. So it's just changing essentially the inner point mass.
They are massless.
Yeah.
So thank you for this very nice talk. One thing that I was curious was in the last panel, you were showing that you are able to unbind more from the red supergiant, less from the blue supergiant, which makes sense because it's much more compact. But I always thought the yellow supergiants could potentially be something in between. So why do you unbind less from a yellow supergiant?
So in this case, this is actually I just kind of picked 3 random ones because this is from Rodrigo Fernandez's paper in 2018. That yellow supergiant is pretty peculiar. It's like strangely compact. Relative to the blue supergiant. So I agree. I think if you did a more of a population synthesis of this, it would be somewhere in between. Thanks.
I think we've got time for 1 or 2 more. I see one. Yep.
Thanks for a really nice talk. I'm curious if you've thought about the sort of type 2P supernovae and some of them that have some sort of CSM mass loss, and how that might connect with this overall picture that you're having
Yeah,
here
like if you have failed supernova into, I've thought of it, not in any way that, because obviously like this actually isn't dealing with any, I mean, self-similar solutions can't have ejected mass. It's all bound in this case. So what you'd say is that the shock reaches the stellar surface, it accelerates, and that's where you start unbinding mass. But yeah, I think that would be interesting, and it's something I thought about, and I think should be done numerically for sure.
Awesome, thanks.
Okay, let's thank Daniel again. Okay, is it all good? Yep, great. So our next speaker is Kaustav Das, who will be talking about the lowest mass stars that explode as core collapse supernovae. Please take it away.
Thank you for the organizers for the wonderful conference. Good afternoon, everyone. I'm Kaustav. I just recently finished my PhD at Caltech a month ago, and will be starting as a Thank you. Yeah, so I'm excited to share some exciting results about the low mass end of core collapse supernovae, in particular the low luminosity type 2 supernovae. So all of us are familiar with the stellar evolutionary picture that if you have a star which has, say, less than around 8 solar masses, you're likely to fuse up to carbon-oxygen and then end your life as a carbon-oxygen white dwarf. On the other hand, if you have a star which has more than around 12 solar masses, you're likely to fuse all the way up to iron, form a red supergiant, and end your life as an iron core collapse supernovae, leaving behind a neutron star or a black hole. So a natural question then is, what is the mass boundary between the formation of a white dwarf versus the formation of a neutron star? So to understand this, we need to sort of understand what happens to the fate of the stars in this 8 to 12 solar mass range. So stellar evolution predicts that they could follow the track that I mentioned at the top. They could also follow the track at the bottom. Stellar evolution models also robustly predict that another possibility is that you could fuse up to oxygen, neon, magnesium in the core and then form something called a super AGB branch star, which could then either end its life as a heavy white dwarf, as a heavy oxygen neon white dwarf, or explode as something called an electron capture supernovae, where you have the magnesium neon atom sort of triggering a collapse of the core. So the second question then is, do these stars explode as iron core collapse supernovae from red supergiants, or do they explode as electron capture supernovae from the super AGB stars with oxygen neon cores? So another reason they are very important is that even though it's just 4 solar masses, because of the power law nature of the initial mass function, they actually account for almost half of all massive stars that explode. And naturally, thus, they are very important in our understanding of the star formation rates, whether they form electron capture versus iron core collapse supernovae is important to understand galactic abundances and so on. So the next important question which sort of comes up is that what are the observational classes then of 50% of all massive stars that explode that should belong in this mass range? So theoretically, 8 to 12 solar mass range are very hard to model. For those of you who have worked with stellar evolution would know that. I won't go into the details. Also from an observation point of view, the idea is that you'll have a smaller core, you'll have lower explosion energies, less nickel that's synthesized, and as a result, the supernovae are a bit harder to observe. So we need a systematic, high cadence, deep, volume limited supernova survey to look for these objects. So I'll talk about a couple of volume limited surveys which I was associated with for my thesis. So one is the ZTF Census of the Local Universe survey, or the CLUE survey. So as part of this survey, our goal was to spectroscopically classify every transient that's discovered within a local volume of 150 megaparsecs. And as part of this, we classified over 1,700 supernovae. And the survey did very well. One of the limitations was that as we went to the 1920 faint magnitudes, sort of the spectroscopic completeness fell down to around 75% or so. And sort of the next goal was to try to achieve very high spectroscopic completeness, including for the very faintest supernovae that ZTF discovers. And the successor of this was this survey called the CATS 150, or the Complete Astronomical Transient Survey within 150 megaparsecs. So as part of this, we leveraged this new spectrograph called the Next Generation Palomar Spectrograph. And the goal then was to achieve high spectroscopic completeness even for the very faint end. This was achieved mainly with the NGPS and also others in the ZTF team providing spectroscopic resources like Igor, Dan in the room. And then as part of this, we achieved a spectroscopic completeness of over 97% for across all transients, including the very faint ones. And as you can see, most of the supernovae that we have in a volume limited survey are usually this class of hydrogen-rich supernovae, which should sort of be the focus. So I'll mainly be focusing on low luminosity type 2p supernovae, but all the papers talk about all type 2p supernovae across this volume limited surveys. So for those who are not familiar, type 2p supernovae are those which are hydrogen-rich, retain a lot of hydrogen at the time of explosion, and sort of have this plateau as the photosphere sort of passes through the recombination front. And low luminosity I define as those which have a peak brightness fainter than -16 magnitude. I'm happy to discuss more on the exact cut. So as part of this project, we compiled the largest sample of hydrogen-rich supernovae of around 330 of this. And as part of this, we have around 36 low luminosity 2p supernovae, which is almost 3 times what we had in the literature. And as part of this, we then put very strong constraints on what the faint end of the core collapse supernova luminosity function should look like. We find that around less than 1.5% of type 2p supernovae are fainter than -14.5 mag. We produce volumetric rates of the supernovae by using very systematic simulation of this entire volume limited survey and trying to reproduce what we have in the actual counts. And then the main takeaway point is that this low luminosity 2p supernovae can account for less than around 9% of all core collapse supernovae. So they clearly cannot account for the fate of all 8 to 12 solar mass progenitors. This was a bit surprising given that you expect 8 to 12 to account for half of all massive stars, and then type 2 supernovae are sort of the majority of core collapse supernovae. So as part of this work, we also did very extensive light curve analysis using radiation hydrodynamic model grids from Takashi Moriya. We did semi-analytical model fitting as well. And we find that sort of there's a strong correlation of the peak luminosity with the explosion energy and the nickel mass that's produced in the supernovae. And overall, the explosion properties are consistent with either coming from an 8 to 12 solar mass red supergiant or a super AGB star. I'll just highlight a few other light curve interesting results that we've got from the light curve analysis. One interesting thing we found was that a lot of this low luminosity 2p supernovae, for some reason, had a positive slope. It's not super clear why. You expect the plateau to be sort of either flat or decline over time. So this was one interesting thing we found. Another result we found was that there was no strong correlation between the duration of the plateau and the peak brightness of the supernovae, which is sort of a strong prediction for single star models. So a possible explanation for that could be that some of this are in binary systems where your outer hydrogen envelope has been partially stripped. Also, another goal was to sort of look for very low nickel mass supernovae where you have a sharp drop sort of from the plateau of the supernovae to the tail. And the idea is that if you have some sort of a fallback supernovae forming a black hole, you'll have the nickel, which is very in the inner part of the star, will also fall back to this black hole, and you'd end up with almost zero nickel. So we have a couple of candidates with a sharp drop from the plateau, but the limits are not deep enough to rule out very low nickel mass. Something which LSST would be amazing for. Coming to the second question which I raised was, are this low luminosity 2p supernovae then iron core collapse supernovae, or are they oxygen neon magnesium core electron capture supernovae? So in terms of the photospheric properties, it's very hard to distinguish them because both of this have this 8 to 10 solar masses of hydrogen envelope and sort of look very similar during the photospheric phases. So one game that you can sort of try to play is that you wait for a few months when the photosphere has sort of receded closer to the core. And there the idea is that the expectations from a SAGB star versus a red supergiant star are expected to be different, primarily by the absence of helium shell elements and oxygen shell elements in the late time spectrum. So this is based on models by Anders Jerkstrand. And then as motivated by this, I had a program with Keck to get systematic sample of low luminosity type 2p late time spectrum, and we got 17 supernovae with this late time spectrum, and then we wanted to sort of assign how likely it is to be an electron capture based on the absence and presence of some of this helium and oxygen shell elements I just talked about in the last slide. And we find that there are at most 2 candidates for electron capture supernovae for which the line diagnostics are sort of matching the electron capture supernova scenario more than the red supergiant scenario. But then the line widths of these lines are almost twice that of what the models predict. So, so we give this sort of as like an upper limit. So since this was carried out in a very systematic manner, we give an upper limit on what the rates for electron capture supernova should be and what this implies in terms of a window of SAGB stars. So the idea is that to the left you have heavy white dwarfs, to the right you have this red supergiant sort of forming regular iron core collapse supernovae, and in the middle you have this super AGB stars electron capture supernova window of at most around 0.06 solar masses or so. So as part of my thesis, so I talked about this hydrogen-rich classes of supernovae. So we know that, as was mentioned by many people in this conference, that most of the massive stars we know are in binary systems, and a large fraction of them are actually interacting enough where your outer hydrogen has been stripped off. So I looked at several classes of hydrogen-poor supernovae with a particular interest on the lowest energy, the lowest nickel mass stripped envelope supernovae in these ZTF surveys. And I tried to characterize their explosion properties and their rates. And overall, we find that even if we sum up their rates, which is expected since this hydrogen-poor supernovae is supposed to be a smaller subset compared to the hydrogen-rich supernovae, cannot account for the fate of all these 8 to 12 solar mass progenitors. So some of the theoretical explanations could be that maybe the lower mass boundary is not actually 8 solar mass, maybe it's a bit higher, maybe it's around 9.5 solar masses. It seems to be consistent with the energies that we get out of the nebular spectra from the line widths. Maybe cores of some of this 8 to 10 solar masses sort of just fail to explode, or maybe they form this heavy white dwarfs. Maybe they explode as other classes of supernovae. Maybe they explode as more luminous supernovae. Maybe they undergo stellar mergers, as we heard about yesterday, and then show up as more luminous supernovae, or also due to CSM interaction. On the observational side, there could be some biases. For example, we expect that the supernovae to be a bit fainter, where we usually suffer from low spectroscopic completeness. It's possible that maybe we have not yet seen some of this very faint supernovae, as ZTF is, for example, for supernovae which are as faint as -13 meg. ZTF is sensitive up to around 20 megaparsecs. Again, this is something which LSST would be very useful for. And another possible observational bias is that some of this supernovae could be dust obscured. So this was based on also a student of Mansi's who found that it's possible that up to 40% of core collapse supernovae could be heavily dust obscured, and some of the most dust obscured amongst those were this class of transients called ILRTs, where you had 3-4 magnitudes of obscuration, which some of the optical surveys would sort of miss out on. Yeah, so with this, I would like to end here. Thank you.
Okay, thank you. I think we have time for one question. Anna.
Hi. It's very non-loud microphone. Anyways, thank you for the great talk. Very interesting stuff, especially on the observational side. I was wondering, have you considered binary evolution in any of the progenitor stuff? Because I've looked into this like way back when, and I remember that potentially binaries could widen this gap in which you could get an electron capture supernova. So I wondered if you looked at that and what kind of influence that had.
Yeah, that's a good question. And yeah, I have tried to look for a lot of those. So the idea is that I talked about the single star showing up as very low energy, low nickel mass systems. But even through the binary scenario, the idea is similar. You would expect a low energy iron core collapse or an electron capture supernova scenario. Those are hardest to find because they are faint and then also very fast evolving. So we do have a few objects, like a couple of 2 or 3 objects, which are sort of well studied in the ZTF sample. But then there's possibly heavy observational bias against them. So that's sort of something which I'm currently working on to try to figure out exactly how much observationally biased we are, or can they possibly explain some of these events. In particular for electron capture supernovae, which are in binary systems, we do have a lot of this very fast evolving faint stripped envelope supernovae, but from what I understand, it's very hard to differentiate them from, say, some of these things like an ultra strip supernovae, which you have very low helium stars like 2.5, 2.6 solar mass. When they explode, you just have like 0.3, 0.4 solar mass of ejected material. You expect the same for like a electron capture in a binary system. So I guess those are also candidates with like very low energy, 10 to the power 50 ergs or so. But then it's hard to differentiate between, again, the low mass iron core versus the binary electron capture.
Thank you again, and let's move on.
Spoiler alert.
Post-explosion binary interaction in supernovae, population models inspired by supernova 2022 JLI. Yeah, over to you.
Thank you. So can you all hear me? I guess so. So, well, that's the title of my talk. I'm Andrea Ercolino. I'm a PhD student, well, not for long anymore, at the University of Bonn. And, well, this is the title of my talk. And I want to start off with something that we've just mentioned, which is that we now know that binary evolution really affects the majority of the life of the majority of massive stars. Actually, it's something about 70% of massive stars are expected to interact some way with a binary companion. Whether they, let's see if the laser works, whether they donate whether they donate mass to the binary companion, which means that they will lose some of their mass, whether they're accretors or some of them even merge, as Carolina showed in her poster. The single stars are only about 29% or even less. So this is only like a small fraction of all massive stars that finally reach core collapse, basically by not have being affected by their companion. And what's more is that once you also look into the demographics of the different types of core collapse supernovae, while we do see that still the majority is dominated by the hydrogen-rich type 2p supernova, and just smaller fractions being the hydrogen-deficient 2b's and then the hydrogen-free 1bc's, we still find that this fraction is still too high compared to what we would expect with single-star evolution. Indeed, you can change some parameters like wind mass loss rates, but overall what happens is that this relatively high fraction, if you try to tweak with the winds, you will then get with, in trying to replicate them with single stars, you get in contradictions with, for example, the upper mass limit observed from supernova, from type 2 supernova progenitors from red supergiants. And this led Nathan Smith in 2011 to actually say that binarity is a key ingredient to explain such a large fraction of stripped envelope supernovas, so the 1bc's and the type 2b's. And there's also recent works that also suggest that interacting supernovae may also be driven by the binary interaction in the late phases of the evolution of the massive stars. What I want to focus on now, however, is actually just on the donor stars. What I want to really focus on is the fact that when they explode, they have a binary companion orbiting nearby. And we do have many cases, well, it's like 6, but we have several cases in which after the explosion, we do find a surviving binary companion. And this is very important because it gives us a very powerful tool to constrain models of binary evolution, which are very prone to larger uncertainties, perhaps even, perhaps a bit less than single star models, but that's a bit of my opinion there. So what I want to say, what I want to show you now is what do we expect to occur when you have a supernova explosion, indicated here by this very creepy star, and when you have a binary companion over here, which, by the way, you'll find it is in the Eben and Tutkov paper from 1984, even though it was from 1A supernova, but it's a nice cartoon nonetheless. So imagine now that you have a binary system in which you have the supernova progenitor and then a main sequence companion. One of the two stars explodes, and now its ejecta is basically rammed into the companion star, which there is some 3D hydro simulations there. The colors are a bit funky, but okay. At the same time, the supernova progenitor also produces now a compact object which receives a kick, which will change the orbital configuration. Now, because of the ejecta ramming onto the companion star is thrown off of thermal equilibrium. What happens then is that the star is basically inflating in a very short time scale, can reach even something like hundreds or even thousands of solar radii, just because it's brought out of thermal equilibrium by this impact. As the cartoon already suggests, though, you may think that then there may be some kick direction and magnitudes such that the new orbital configuration may achieve like periastron passage within this very extended and loosely bound region on the companion star. When it does, what you would expect is that you have the compact object flying here, and then there will be a lot of material that it will sweep through, and then there will be a lot of radiation, especially hard radiation, being ejected as a consequence. What you would expect, though, is that since this is a orbital, an effect coming from just the binary here, this should give rise to periodic effects into the supernova. And just because I will say this a couple of times, we refer to this phenomenon as compact object companion interaction, because otherwise, which is the complete name, which is a bit of a mouthful, so I'll just say CCI for short. And what we found is this little supernova, 2022 JLI, which has this very interesting 12.4-day modulation, which is kind of interesting. You don't see many supernovae exhibiting this, except some superluminous supernovae. But now this supernova is actually pretty interesting for a variety of reasons. Not only do you see this oscillation in the light curve, you also see it in other things. For example, gamma ray flux, where gamma ray is observed from this supernova, and they have a 12.4-day modulation. So every 12.4 days, the gamma ray flux goes up and goes down, which makes sense if you think about a binary system, and each time you have the compact companion just sweeping through the material. Similarly, however, this is a 1C supernova, and yet after 50 days, an H-alpha line appeared, and the H-alpha line had a 12.4-day oscillation in velocity. You may think of this by seeing the binary system, and you're just seeing the massive star having basically being excited, sometimes going towards you, sometimes back, well, once every 12.4 days, basically. And so all of these ingredients, all of these observations together is really telling that perhaps what we're observing right now is a binary system. And so the question that I want to answer is 2022 GLI a unique supernova, or is there perhaps a family of transients that we have not yet discovered? And if so, how many of them should we expect? And so to do this, we have a large detailed grid of binary models that were developed at the University of Bonn by Harim Jin. Now, the grid of binary models is very extended. It's, in a sense, complete in its coverage of the primary mass, because it covers the entire parameter space to produce co-collapsed supernovae. And the orbital parameters are also complete in terms that they cover the entirety of the binary interaction parameter space, from the tightest binaries which merge at ZAMS to those that are so wide as to never interact. We put all of these detailed models in a population synthesis code, and then we use some prescriptions for the kicks and also for the for modeling these expanded phase of the companion star to assess how many times we would expect the compact object to basically fall within the atmosphere of the companion. And so what I want to shortly show now is what supernovae would we expect to have these undulations. So for example, these, if we go to very wide binaries, here I'm showing you what happens with a 14 solar mass star, and you have a different initial binary orbital separation or orbital period, and different mass of the companion. If you go with, if you have a 14 solar mass star with a very wide binary, well, it will explode as a type 2 supernova because there is no binary interaction whatsoever. But at the same time, since the orbit is very wide, kicks will likely unbind it. So there will be no periodical behavior, no periodical interaction with the compact object. But as you move tighter, what happens is that you strip the supernova progenitor more and more because mass transfer. And eventually you produce stripped envelope supernovae. And at the same time, the orbit at the very end is very tight, which then makes it easier for kicks to not, well, it makes it harder for kicks to unbind the orbit, and therefore it makes it more likely that you may give rise to this sort of interaction process. And so in a sense, this interaction that we have been discussing is more likely to occur in hydrogen-poor supernovae and should be very rare in hydrogen-rich supernovae. How much? Well, we think that this is around 3 to 27% of hydrogen-poor supernovae, which should be affected by this. But this is a bit of just a theoretical estimate. We are just saying how many supernovae would have this interaction process, but we're not making a claim on how easy it would be to observe, because we're not making any estimate of how luminous this interaction process would be. But regardless, what this is suggesting is that perhaps observations so far may not actually have detected these interaction process before. For example, the cadence may not have been enough to detect these undulations, and also the observational depth may not have covered these little bumps. And so this is why we kind of look forward for the combined operations of all the amazing transient surveys that we have, especially with the Argus array, LSST, and ZTF, but all at once. Like there's no single transient survey that does this. It's with the combined efforts that we may actually detect more of these transients. And to give you an example of expected orbital periods that we find, well, it's quite large. So it's something from between a few days to even up to 1,000, which is not really constraining. But what I want to highlight here is that we have 3 non-superluminous supernovae with these undulations, 15 AP, 22 JLI, and 22 ESA, which, well, a bit trivially fall within our observed, our inferred distributions from the population models. But having this means that we can then go back and say, okay, we have these constraints on these supernova. Let's see how many of our binary models would basically match these constraints. And what we find is that we actually find a plethora of binary models that can potentially give rise to the progenitors, well, to the observed undulations in these supernovae that you see here. And what we can then do is to look at what's the property of the companion star. Knowing the properties of the companion star means not only knowing its mass, but also its luminosity, its effective temperature, and so on. Which means that if we know how the companion star of the supernova would look like after the explosion, we can then make claims on whether or not we should be able to still observe the companion star today. And so we made predictions on the brightness, for example, of supernova 2022 JLI's companion star. And here I'm reporting the J-band magnitudes with the VLT's Hawkeye instrument. And we have an observational depth limit of 23 magnitudes with a 5-minute exposure. And what we have is that we think that the companion star will shine with basically with a magnitude above 23 and a half, so should be observable. And so if one then goes tomorrow, next week, within the next few years at best, and go on the lookout for the surviving companion, we can learn a lot about, well, not only stellar evolution as a whole, but also whether or not this CCI, this interaction process, is actually, modeled correctly, or also if there is perhaps dust formation which may actually prevent us from observing such a companion. And yeah, that's all I wanted to talk about, and thank you for your attention.
Questions? Yeah.
Hi, thanks for the really nice talk. When the star goes supernova and the companion basically gets the mass of the supernova ejector, would you say the companion might look like a red supergiant for a bit? And perhaps if the supernova remnant is a neutron star, do you think you could perhaps see something like a TZO, like a Thorne-Zwicky object?
If the kicks are just right and the compact object just flies inside, then that's how you create a Thorne-Zwicky object. But that's like a smaller parameter space, just in terms of cross-section of the kicks necessary to achieve that. But that's a possibility. You can definitely produce that eventually.
It's really interesting. Thanks.
Thanks.
Quick question. Yep.
Thanks a lot. Really cool talk. I'm wondering, what is the time scale on which the companion gets inflated, and how it compares to the orbital time scale?
So in the original papers by Ryosuke Hirai et al. From 2018, 2021, 2023, which I've listed here, the expansion seemed to happen on a dynamical time scale. So it's something in the order of hundreds of days at best, but it can be also shorter, because you also have to imagine that this was initially a main sequence star. So the dynamical time scale is sometimes in the orders of minutes or hours. So the expansion is basically immediate.
But would you then expect the amount of mass to, how much mass would be there in that inflated envelope?
You mean in the ejecta that rams into?
No, and the part that's then later accreted every orbit, like how much mass is in the envelope that's inflated?
Okay, so this fluffy region here, it would not have more than a few tenths of a solar mass. It's very extended, but very diffuse. And so you would not expect there to be a significant drag that would, for example, produce a Thorne-Zwicky object.
That's what I was thinking. Okay, thanks a lot.
Scale.
Thanks.
Thank you again. Okay, and our last talk before the break will be from Anjasha Gangopadhyay. Said that. Ah. Okay, yep. Yeah, so our last talk will be by Anjasha Gangopadhyay, who will be talking about interacting type 1bn supernovae with ZTF. So, yep, over to you.
Hello, everyone. I am Anjasha Gangopadhyay. I'm a postdoc in Stockholm University, and this is a presentation on type 1bn supernovae from the ZTF. So this is presented on behalf of a larger ZTF collaboration. So I think Ragnhild briefly talked about interacting supernovae, but these are the ones in which they interact with the dense circumstellar medium, and they show narrow emission lines in their spectral profiles. So if you look into this classification of the core collapse supernovae, you see the ones that have this N in their title, or that ends with N, shows narrow emission lines. And if it has narrow hydrogen-rich lines, then it is a type 2N. If it has narrow helium-rich lines, then it's a type 1BN. And if it has narrow narrow carbon and oxygen lines, then it's a type 1CN. And in this presentation, I will be briefly speaking about a group of type 1BN supernovae, which shows narrow helium emission lines in their spectrum due to interaction with the helium-rich circumstellar medium. Now, the Zwicky Transient Facility has a survey called Bright Transient Survey, which is a magnitude limited survey, and it has classified about 10,000 supernovae as of July 2024. And among this whole survey, we find that there are only 40 supernovae of type 1BN. So these are very rare events, and studying each of them is very useful. Thus, we have a lot of data from Palomar telescopes, the Nordic Optical Telescope, the Keck Telescope, and Liverpool Telescope for this analysis. And let's start looking into the light curves. So if you look into the light curve space, if you separate the population based on the rise times of these supernovae, you find on the left that there are these beautiful bell-shaped symmetric light curves, while on the right, you see the ones that have this precursor activity, weird bumps on the towards the decline. So this basically represents that among this class, there are two different populations of the light curve. Now, they were traditionally believed to be the ones that rise fast, decay fast. So this is one from the Griffin's sample, which you typically could match with the ones on the left. However, we see that the ones on the right are very different from what we traditionally believe them to be. Now, what we tried to see is to check for correlations between the rise time and decay time when the flux decreases to 50% of its value. And we find that they are strongly correlated around the peak. However, if you go to the very late time light curves of these supernovae, like here, you see that there is a huge diversity in the light curve. And this is basically due to different circumstellar medium configuration. Now, what we tried to do is we tried to color code the peak G minus R color with the absolute magnitude. And what we also find here is that the brighter ones are not always the bluer ones. So basically the colors do not directly trace to the brightness of these supernovae. And when we looked into the color evolution of these supernovae, so these are quite homogeneous around peak, while if you go to the late time colors, they show a huge diversity. So we cannot really map the color variation as a sample because of a very diverse circumstellar medium configuration. But what we see for these are, like if you do a cumulative distribution function of the rise times of these 1B and 1CNs with the general hydrogen poor stripped envelope class, then you can see that the rise time wise, they are actually fast risers than the traditional 1B, 1Cs. Now, what we also wanted to do is to construct a template light curve to represent this as a population. So for this, we compiled these 40 light curves of type 1BN, and we used a method called using stretch factors, which preserves the shape of the light curve, and we generated a template light curve, which could be representative of this class. Now, this template light curve also shows here, we compared it with several other templates of the normal stripped envelope class and the interacting class. And we find that they are quite fast risers and fast decliners than the normal stripped envelope class, which are not interacting. However, they show quite a diversity during the late phases, which could be seen in the error bars that you see here. Now, we also tried to do the spectroscopic analysis of these group of supernovae. And as you see here, the spectra typically consists of the helium narrow lines. And the helium narrow lines here have two classes. Basically, some of them show this narrow P Cygni kind of structure, while some of them shows this narrow emission kind of structure. Now, for analyzing this, what we did, we fitted a number of Gaussian and Lorentzian functions to find out what is the combination of the Lorentzian and Gaussian that best fits our observed parameter. And we find a Bayesian inference correction factor, which gives a measure of how good the fit is. And also, our aim was to classify whether our object belongs to this P Cygni subclass of these objects or the emission subclass. So we estimated a delta BIC factor, which is the difference between the emission and absorption, and find out how good or which class the supernova belongs to. So when we did this, we found that about 9 of our sample belongs to the P Cygni subclass, 9 of them belongs to the emission subclass, and we refrained from classifying some because they have the delta BIC less than 6, which means that we are not confident enough to classify them to a particular subclass. Now, what this physically means when we have a P Cygni or an emission subclass? So one probable explanation is the geometry. So let's assume there is a supernova ejecta which interacts with the circumstellar medium. And if we see it face on, then we could see an emission profile. However, if we see it edge on, then we could see a narrow P Cygni coming in. This could be one of the explanation, or it could be an interplay of optical depth happening, which gives rise to this emission and absorption profiles in the spectra. So what we also wanted to do is, so when we have a spectra of this type 1b supernovae, what is the classifying criteria, or how do we classify them as type 1b supernova? So for that, what we did, we found the narrow component and the broadest component of the fit, and we find the KDE crossover point of these two populations. And we find that the narrow component peaks about 1100 km per second, the broad component peaks about 5000 km per second, and the typical crossover point of these two populations are 2700 km per second. So from here, we tried to say that whatever is below 2700 km per second, if you see a narrow helium line, then you could safely kind of classify this as a type 1b supernova. Now, we also wanted to see how the late colors behave. And so this is the helium line velocity evolution. And we mapped it with the G-I colors from the synthetic photometry and tried to see if the late colors can show a trend in the helium line evolution or the velocity evolution. And when we tried to do that, we found that some of the ones that are bluer showed lower helium velocities or FWHMs, while as we move towards the redder colors, it shows broader helium FWHM. So this could be that these are still in interaction zone, and this could be that they are moving towards the ejecta phase when interaction has died down. Now, our aim now is to model the light curves. So this is one of the cases that we have previously published, where we tried to model it with the simple Chatsopoulos approximations, where it's assumed that the circumstellar medium is a wind-like or a shell-like structure, and we tried to fit the multiband light curves. And from here, what we find is that they have very low nickel mass, they have very low ejecta mass, and they have very low circumstellar masses as well. Then the question is, what kind of stars gives rise to these kind of explosions? Now, as you see that there are a lot of light curves with diverse asymmetric structures, the ones on the right that I showed. And for those, if we fix the circumstellar medium geometry, it becomes really tricky. So we have this new formulation from Nikhil, which is now in archive, and now you can see that we don't fix the circumstellar medium configuration, and we can change the, so it's a time-varying configuration of circumstellar medium density and velocity, and we tried the same object with 8 combinations of different circumstellar medium models that are available, and we find that the wind model is the most favorable one, which is same as the previous case, but with similar, and we get almost similar parameters using this for this supernova as well. And we have recently worked on this object, which is the 1CN with Kaustav, and this also shows that you see that the nickel mass and ejecta mass of these classes of events are really, really low. So from all kind of light curve modeling, we find that we get really low ejecta masses for these. So if you look into the single star picture, it could be Wolf-Rayet stars, but we cannot account for such low ejecta masses using a single Wolf-Rayet stars probably. So for that object, we also used the non-radiative LT transfer models from Luc Desart, and we find that a very low mass helium star, like a 3M solar helium star in binary companion, kind of matches our observed profile. And this gives us the idea that low mass helium stars in binary companions can actually be progenitors for these group of supernovae. So probably we can come to this conclusion that the ejecta masses are not high, and probably these are not single stars. And as Andrea mentioned, so Andrea also has this theory of this binary population where they find that there are two stars, and where one of them is a helium star, and a second mass transfer occurs when they form a circumbinary kind of disk around the primary star, and one of them explodes as a supernova in this circumbinary disk. And this is probably one of the possible progenitor channel for this group of supernovae. However, there is this event PS112SK, which occurred in an elliptical bright cluster galaxy. And this is like one of the events which occurred with a very low level of star formation. And they proposed that the white dwarf binary systems could be actually the possible progenitor channel for this. So this is only one case, we don't know, but still we cannot completely rule out this possibility of this white dwarf mergers. So to end with this, we see now that they are not homogeneous as previously believed. So they have really asymmetric circumstellar medium, and their light curves could be really diverse. The spectra have two subclasses, one with the P Cygni and one with the emission subclass, but we do not know the physical origin. Probably it's a geometrical effect of the circumstellar medium. Most light curve parameters for them are not correlated. So they have rise and decay times, which is strongly correlated around peak. But if we go towards later phases, nothing correlates with each other. So this is probably a very diverse CSM configuration. We can typically say that if we have a 1BN supernova, which is a narrow helium emission lines, and the line width is typically 2000 km per second, probably we can safely classify them as a 1BN supernova. The progenitor is a big question. Probably when I'm running the models over the full grid and compare with Andrea's theoretical models, we have an answer for the grid or for the whole population. But as of now, it could be a single Wolf-Rayet star which we probably can rule out, but not sure. It's most likely in binary, and we cannot completely rule out the thermonuclear origin as well. So yeah, thank you. That's all from my side.
Any questions?
Hi, really interesting talk. I'm curious about your use of the KDE as a kind of empirical classification metric. Why did you choose to do it like that?
Yeah, to be honest, I was searching for ways to find out is there any method to robustly classify, like a parameter to find out how can we classify these kind of supernovae. So we always know that they have some broad component which comes out due to ejecta and some due to circumstellar medium, which is narrow. So I thought that maybe if we do a probability distribution function of the narrow and the broad component, and if we can find a junction or a boundary which connects these two populations, then we could say that, okay, whatever is below this in the narrow zone of the PDF could be a classifying boundary. But if you have better ideas, I'm open to it.
Thank you.
One more, yeah. Right up there.
So thanks for the interesting talk. One question that I have is with the spectra. So are the spectra always taken at peak light, or is there some variance in when the spectra are taken? Because that also means that you will have a different velocity profile, which may have been sampled at the time. Could that influence your classification that by modality that you see?
Yes. So when I say I separate it into P Cygni and emission subclass, this means we are separating it at peak. I should have mentioned that. So the spectra is only at peak. So, but if we move towards the later phases, then for many of them, the P Cygni subclasses actually vanish, and they start to get broader in profiles, it's the time when ejecta starts to show it in the, or ejecta comes in picture. So this is at peak, the classification. Yes.
Thanks.